afternoon. So I'm the CEO of Carrousel Digital. What we do is entangled photon communication, photonic router, and teleportation. We just do the IP, so we're looking to license our technologies. So entangled photon communication, what is it? It's a step forward to a quantum communication, to QKD, sorry. But here we transmit classical data between 2 points, A and B, using entangled photons. So how it works is that here we have an entangled photon emitter, you see at the top, which is sending one photon to A and another one photon to B. And the photon arrives first in A, and then the photon arriving in B, just after the sister photon has arrived in A, is being amplified, and its polarization is being read in B with interferometers and polarization direction detectors. So when the photon arrives in A, we encode it with the information. What we do is that we detect basically its polarization on an angle with an angle and a phase, which is dependent on the information you want to transmit. We do that by using linear optics. So here you see at the bottom a rotator, which will send the direction of the photon, you see, from E1 to E2 according to the data you want to transmit. And then we use Pocal cells to change the phase, to put some dephasing between the two directions, which further enlarges the alphabet on which you can encode the data. At the same time, well, in the meantime, the photon has traveled to B and is being amplified. So now we don't have one photon. We have, let's say, 10. We have a million photons, and we use regular polarization and angle and ellipticity reading. So this will have transferred the information. The thing is that what happens in practical world is that photons do get lost. These are the classical decibels people were talking about before. So when a photon is lost arriving in A, the thing is that the sister photon arriving in B may have been entangled to a photon which was lost while traveling to A. But the thing is that statistically, a lot more photons will arrive in B with the polarization as they were coded in A than any random number, save for if there is a special polarization in which the photons get absorbed in the line traveling to A. So what we do is that we set a number of identical receive codes over a set number of successfully received photons to detect the state information. So typically, for a 100-kilometer line with a 90% loss of photon, which is about 10%, 10 decibels, then we just need to watch 100 photons, and if you receive more than 6 times in the 100 photons the same letter, then you can deduct that this letter is information that you want to transmit with a probability bigger than 10 to the power 5. So now describe the system. So the system is fast because the information coding the photon in A immediately changes the photon of the polarization of the photon that has already traveled and arriving in B. That's because the photons were entangled. Now we add a security layer similar to quantum key distribution to make sure that the information has not been listened to. Yes. So what we do is that we make sure that the photons arrived entangled near A and B. So what to do that? We just check the arrival time. Once we have determined which 6 photons did transmit the code, we exchange a message, a signed message between A and B, maybe using the same system, saying, okay, well, these photons arrived at this time. What about your photons? And we said, well, we coded the same photons with the same polarization at the same time, so that's fine. That's because so far we cannot control which polarization exactly it's going to be. The photons will be detected. That's a quantum key distribution. So this process is completely random. But if the polarizations match, it means that these photons were entangled. So the thing that, for instance, if people want to listen to the conversation, they can demultiply some photons or hijack some photons, but then the quota of 6 photons will not be reached, and information will not be transmitted. So what we've done, yes, I've already explained. Sorry, the man in the middle. That's it's checking the arrival time. And also checking the polarization of the exact polarization at which the photons arrived. And there's another tweak to the thing, which is a problem as well, similar to QKD, is that if the exchange, the message where we exchange between A and B is not quantum safely encrypted, signed, it means that anyone, in fact, who has the technology could hijack your encryption keys and put a man in the middle. Usually these people would have to have access probably to some very powerful computers, but still, if you don't have a quantum safe key to sign your message, which where the time of arrival and the exact polarization of the photons have arrived, if you don't have that, your system is not quantum safe. So what we have is that we have a quantum safe signature algorithm, which we have already also patented, which is what we do is that we put in the message to be signed a secret number shared between the two parties, A and B. And therefore, this allows us to use one-time keys to decrypt the hash. And one-time keys cannot be computed or guessed even by powerful computers. So this makes our system quantum safe. So how to transmit the information? So you can have a 200-kilometer transmission using optical fibers, or you can have free space satellites. Where you can transmit photons to a 500 kilometers low orbit space with only 12 decibel loss. So this makes it compatible with our system. So now let's go to the our second device. What happened until the previous presentation arrived is that for quantum key distribution, you had to have a link, optical fiber link between every modem. So that was a problem, and I thought this is not too good for entangled photon communication. So what I've come up with is a photonic router, which is one router to connect multiple terminals with only one optical fiber between the router and each terminal. So it's very simple technology, and it's a passive router, so you don't need to power it up. The way it works is that the router is routing the photons according to their color. So here, for instance, if you have a photon in blue on the top computer, it will be rerouted by the router to the computer just below, and that is the way it works. So it's using inside the router, you have the demultiplexers, which change the route of the photons from the incoming fiber to the appropriate fiber, which is connected to the appropriate demultiplexer, which is connected to the proper port. Right. Yes, so I've already done that. This also can be used to leverage on your optical fiber network because you can use, as the professor said it, regular fiber networks, provided you don't have any classical passive optical router in it that will lose the photons. You can build a worldwide ground cover satellite with 600 satellites at 500 kilometers altitude to link the world. And you can also link distant CPUs because the distance is the process is so fast. You could use that to link CPUs. So now let's come to our third patent. We've acquired the patents, the US and France and other places, mostly US and France for the two previous designs. So now this is just patent pending. So this is long distance quantum teleportation. I remember when I first made the presentation on entangled photon communication, I talked to a guy who became crazy and said, "What, you don't use photon entanglement?" And I was like, "What is he talking about?" And but then I figured out it would be interesting. People are interested with that, and I've come up with this scheme, which uses which was better using the entangled photon communication. So what we create on the first step is an optical EPR channel, so Einstein-Podolsky-Rosenberg channel with two photons in A and B, which are entangled. The way it works is that we use optical photon detectors. Well, this exists. So these are non-destructive optical photon detectors, which are cavity-based with a rubidium atom inside, and they detect photons with better than 95% accuracy without changing them or changing them very little. So once we have the photons we detected, here we use our communication to say, hey, I've just seen a photon arriving at this time, and to the other party in B, and the other party says, okay, well, I've seen the sister photon arriving at the same time. So this means that the photons were entangled. So the information comes back. You see the little trick here, because while the systems talk and send this information, you need to put the photons in an optical fiber or in memory to wait a bit. And once you've got the answer, either the photon is paired with another photon that arrives at the same time on the other side, and then you release the photon and you say, well, this photon is entangled to another photon on the other side. Either you discard the photon and send them to an exit. So now we've created an EPR channel, so up to 200 kilometers or maybe more, using using satellites or less lossy lines. Then you can use this scheme to do quantum teleportation. So what is quantum teleportation is that basically you send a qubit in A and you want to retrieve it in B. And these are typically these schemes use an EPR channel, which we've already constructed. So in green, you've got the EPR channel system, and which releases in two a photon which is entangled to the photon traveling in 4 towards B. And then we use again one of these rubidium cavities, but it's a slightly different setup, which perform C switch gates, which you can transform into a CNOT gate. And then you do a Bell measurement on you do a Bell measurement on the control photon, and on the incoming photon on PD1 and PD2. And depending on this measurement, you will activate linear optics to get them to do the appropriate single gate to the photon in B, so that the photon after this gate has the same qubit as the photon that was arriving in 1. Yes, that's it. So you've got teleportation, long distance teleportation over satellites or so how non-destructive photon detectors and CNOT gates, how do they work? So here these are details. Fidelity of detected photons is 96%. They work with 780 nanometer photons. They use rubidium 87 in a cavity, and they work with a repetition rate of 576 Hertz. And so, yeah. And the C-flip, this is for the non-polarization photon detector, non-destructive. Now for the C-flip gate, for the control flip gate, control not gate, the fidelity is only 76% so far. That's it.
We have time for a question or two.
So I've been clear enough.
I will ask one as the moderator. I'm not familiar with the term non-destructive photon detection. How is the photon not captured or destroyed?
Yes. Well, the photon, when it travels inside the cavity, it will change the level, the energy level of the atom, but very slightly only. And but this will be enough to change its ability to reflect the second incoming photon. So in one case, it will be reflected at the back end of the cavity. In another case, it will be reflected before, at the entrance of the cavity. So this impedes the control flip.